Imagine a place in space where gravity is incredibly strong, a place where the very fabric of space-time is twisted and contorted. So strong that nothing, not even light, can escape its grasp. This phenomenon is known as a black hole. A black hole is a region of space-time where gravity's pull is so intense that it warps the space around it, creating a point of no return known as the event horizon. Black holes are invisible to us because they do not emit any light. They are like cosmic vacuum cleaners, sucking in everything that comes too close. However, scientists can detect them by observing their effects on nearby stars and gas. When a star orbits an invisible point, it often indicates the presence of a black hole. Black holes come in different sizes, ranging from small to supermassive. The smallest black holes are known as stellar mass black holes. Some are small, formed from the remnants of collapsed stars. These stellar mass black holes are typically a few times the mass of our Sun. Others are supermassive, millions or even billions of times the mass of our Sun. These behemoths are found at the centers of galaxies. These giants lurk at the centers of galaxies, including our own Milky Way. The supermassive black hole at the center of our galaxy is called Sagittarius A*. Black holes are mysterious objects that continue to fascinate scientists and the public alike. They challenge our understanding of physics and the nature of the universe, making them one of the most intriguing phenomena in space. Stellar black holes, the most common type, are born from the death throes of massive stars. These cosmic giants, often tens of times more massive than our Sun, live tumultuous lives. They burn brightly, consuming their nuclear fuel at a prodigious rate. Over millions of years they shine as beacons in the vast expanse of space, their light traveling across galaxies. When a star much larger than our Sun runs out of nuclear fuel, it can no longer support its own weight. The balance between the outward pressure from nuclear fusion and the inward pull of gravity is disrupted. The star begins to shrink and dim, its outer layers cooling and contracting. This process marks the beginning of the end for the star. The core collapses inward and the star explodes violently as a supernova. This explosion is one of the most energetic events in the universe, releasing more energy in a few seconds than our Sun will emit in its entire lifetime. The supernova scatters the star's outer layers into space, creating a brilliant display of light and color. If the core's remaining mass is sufficiently high, gravity will crush it further, squeezing it into an infinitely small point called a singularity. This singularity is a region where the laws of physics as we know them break down. The density becomes infinite and the gravitational pull is so strong that not even light can escape. This singularity where density and gravity become infinite lies at the heart of every black hole. It is a mysterious and enigmatic point, shrouded in the fabric of space-time. Scientists are still trying to understand the true nature of singularities and what happens within them. Surrounding it is the event horizon, the boundary beyond which escape from the black hole's gravitational pull is impossible. This boundary is not a physical surface but a point of no return. Once an object crosses the event horizon, it is inexorably drawn towards the singularity, lost to the outside universe forever. The event horizon marks the edge of the black hole, a region of space where the gravitational forces are so extreme that they warp the very fabric of space-time. Imagine approaching a black hole. As you get closer, you would feel its gravitational pull getting stronger. At a certain point, you would cross the event horizon, the point of no return. Once you cross the event horizon, there is no going back. You would be inevitably drawn towards the singularity at the center of the black hole. Interestingly, an observer watching you from a safe distance would see something different. As you fell towards the black hole, time would appear to slow down for you from their perspective. You would seem to freeze at the event horizon, your image forever frozen in time. What would happen to you if you fell into a black hole? The answer is not pretty. Because of the extreme gravity, you would experience something called spaghettification. As you fell towards the singularity, the gravitational force on your feet would be much stronger than the force on your head. This would stretch your body out like spaghetti. This stretching effect would become more and more extreme as you got closer to the singularity. Eventually, your body would be ripped apart, and you would be reduced to your fundamental particles. These particles would then be added to the black hole, increasing its mass ever so slightly. Section 5. A firewall of energy? Another theory emerges. Some scientists believe that the event horizon is not a smooth, empty space. Instead, they propose that it might be a firewall of intense energy. This firewall would incinerate anything that crosses it, instantly vaporizing any matter that dares to enter. This firewall theory is controversial and still being debated. It challenges Einstein's general relativity, which suggests a smooth passage through the event horizon. However, the firewall theory attempts to resolve inconsistencies between general relativity and quantum mechanics, two fundamental theories in physics. Section 6. Lost to time and space information paradox. One of the biggest mysteries surrounding black holes is what happens to the information that falls into them. According to quantum mechanics, information cannot be destroyed. However, the singularity at the center of a black hole seems to violate this principle. This is known as the information paradox. Some physicists believe that the information is not actually lost, but rather encoded in the black hole's event horizon. This encoding might be accessible in subtle ways, potentially through Hawking radiation, a hypothetical thermal radiation emitted by black holes. Section 7. A black hole. Fun fact: time warps. Here's a fun fact about black holes: they can warp time. Black holes are one of the most fascinating and mysterious objects in the universe. Their gravitational pull is so strong that not even light can escape from them. But did you know that this immense gravity also affects time itself? Because of their immense gravity, time slows down near a black hole compared to time far away. This phenomenon is known as time dilation. Imagine a clock ticking away in space, far from any massive object. Now place that same clock near a black hole and you'll see it tick much slower. This isn't just a theoretical concept, it's a real effect predicted by Einstein's theory of general relativity. This means that if you could somehow survive a trip near a black hole and return to Earth, you would find that everyone you knew had aged much more than you. This is because time for you would have passed much more slowly than for those who remained on Earth. It's like a real-life time machine, but with some pretty extreme conditions. This time-warping effect is a consequence of Einstein's theory of general relativity. According to this theory, massive objects like black holes warp the fabric of space-time around them. This warping affects not just space, but time as well. The closer you get to a black hole, the more pronounced this effect becomes. It has been observed indirectly by astronomers studying the behavior of stars and gas orbiting black holes. These observations provide strong evidence for the time-warping effects predicted by general relativity. By studying the light and motion of objects near black holes, scientists can infer how time is being stretched and compressed. The closer these objects get to the black hole, the slower their clocks appear to tick. This fascinating phenomenon not only deepens our understanding of the universe, but also challenges our perceptions of time itself. So next time you think about black holes, remember, they're not just cosmic vacuum cleaners, they're also time machines. Section 8. Cosmic opposites. Black holes versus white holes. While black holes are regions of spacetime where gravity is so strong that nothing can escape, white holes are theoretical objects that are the exact opposite. They are regions where nothing can enter, only exit. Imagine a cosmic fountain constantly spewing out matter and energy. While black holes are supported by strong observational evidence, white holes remain purely theoretical. They emerge from the mathematics of Einstein's equations but have never been observed. Some physicists speculate that white holes could be connected to black holes through hypothetical tunnels called wormholes, creating shortcuts through space-time. Section 9. The unknowable enigma, black holes in the future. Black holes remain one of the most fascinating and mysterious objects in the universe. They push the boundaries of our understanding of physics and challenge us to think beyond the familiar. As we continue to study them, we can expect to uncover even more secrets about these enigmatic objects. Perhaps one day we will be able to answer some of the biggest questions surrounding black holes. Can we unlock the secrets of the singularity? What happens to information inside a black hole? Do white holes and wormholes truly exist? Only time and continued exploration will tell. Please like this video and support us by subscribing to our channel, Fact Phenom.